All right, so we're going to continue today on algorithm and algorithm analysis, of course, and today with several examples, because that's how you get to understand this kind of stuff, is through examples, because some of it is art rather than science, in that if you choose one input and one elementary operation, that leads to one analysis, which is perfectly valid. And then if you make other choices, then that leads to a different analysis, which may also be perfectly valid. So remember that we have this 5-step process. And remember, we are on Piazza if you have any questions. Let me just make sure that we've got everything set up over there. So remember that there is a 5-step process that I'm giving you, where you identify the input, you identify the input size, you identify the elementary operation, and you determine how many times that elementary operation is executed with respect to the input size. And then finally, something that we'll get into next week, step 5, is you provide a big O asymptotic analysis of that algorithm. We started by looking at identifying the input. If you write good pseudocode, that's going to be automatic. But sometimes there are multiple inputs, and you have to decide which one is the most relevant to keep it simple so that you're only looking at one thing. Then you identify the input size, right? Oops. Oh, sorry. Let me go ahead and get rid of this. Nope, that's not what I wanted. All right. There we go. Let's see, honors. I want this one. Split this right. And unfortunately, it was rendering the wrong version. And open a new window. There we go. Sorry about that. All right. And let me zoom back in here. All right, there we go. So this is where we left off, with identifying the input size. Now, remember that we left off by asking the input of a single integer x, what is its input? And the naive answer is just simply just say 1, because there's only one number, right? Well, and I forget how far we went on this, but oops. Oh, come on. There we go. So certainly I hope that you understand that there's a difference between numbers, right? If I say 5 versus 5,173,847,142, right? There's a difference in the sizes of those inputs. Let me go over here, sorry. There we go. Right? Certainly if I put it into the context of, I'll give you this much money, which one are you going to choose? The bigger one, right? Exactly, that we already have an intuitive notion that one of these is small and one of these is big. We just need a way to quantify what we mean by small and big. When I wrote these down, how many characters did I write? How many symbols did I write? This one, I only wrote 1. This one, how many did I write down? The second one right here. 3. 3 symbols? Yeah, it was, sorry, there you go. I'm not going to count the commas as symbols, though, right? So, 10, right? In other words, what is one of our intuitive notions about how many, or how big each one of these things is? The number of digits is equal to the input size. Because you got to write it down. You got to write it down on a piece of paper to input it into your Euclid's GCD algorithm. You've got to load it up into memory if you're going to run it on a computer. So however many symbols it takes to represent that number. Now, if I were to give you x, how many digits does it take to represent this? Right. Well, if I gave you x was 5, was your answer 5? No. If I gave you x was 5 billion something 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 something, was our answer 5 billion something something something? No. So it's not the value of the number, right? So I like going over this exercise just to remind you about the value of some of the mathematics that you're already familiar with. Let's think of it in terms of the other way around. What if I gave you a number of digits? right? What if I only gave you one digit? What is the maximum value that you could write down? 9, right? What if I gave you 2 digits? What's the maximum value that you could write down now? 99. 3 digits? 999. And you can start to see a pattern emerge here. What if I generically gave you D digits? What's going to be the value now? 9. So D nines, right? But how do we express that as a number? 10 to the D minus 1, right? Basic scientific notation, okay? Now, I was asked, my original question actually worked backwards. If I gave you a number x with a maximum value, how many digits does it take to represent that value, right? And all you need to do is a little bit of math, right? If I say that x has a maximum value of at most 10d minus 1, then you need at most how many digits to represent that thing? All you need to do is solve for d, right? So let's take 1 to the other side. Now, how do I get rid of that 10 so that I just have that d in isolation? A logarithm. What kind of logarithm? Base 10 of x plus 1 is equal to d, right? Forget about this 1, right? We don't like little constants. If you take off that 1 and then take a ceiling, you get the exact same, or a floor or something, you know, just make it a little bit bigger. Who cares, right? So it takes about log base 10 of x digits to represent x. Why was it this base 10? Because we worked in digits, right? And that's what humans have, right? What if we were to work in whatever computers speak in? So computers don't have any fingers or toes. But you can imagine if they did, how many would they have? Computers? Well, for their base system, 1 is, yes, 0 or off, but that base system is binary, base 2. So same exact argument as before. What if I gave you a number of bits? If I gave you 1 bit, what's the maximum value that you could represent? 1 base 2, which is the same as 1 in base 10. If I gave you 2 bits, you could represent 1, 1 in binary. That's why I'm writing this as a subscript of 2. That's the binary version. In base 10, what is 1, 1? Convert the binary to digits. 3. Right? What if I gave you 3 bits, digits? They were actually called digits at one point. 1, 1, 1 base 2 is going to be 7. Dot, dot, dot. What if in general I gave you b bits? Then this is going to be 2 to the b minus 1. Hopefully you see that pattern here. So likewise, when I work backwards, what do I get? Log, or about, log base 2 of x. Right? It's the exact same answer, just a different base system. Does it matter? So, computers work in binary. My tablet, the virtual paper that I'm using right now is base 10. Does that mean that I have an advantage over a computer because I'm using more numbers in my base system? Or does it mean that a computer has an advantage because it's using fewer numbers in its base system? Does that matter for algorithms? If we meet the aliens tomorrow and they have base 5 because they have 2 fingers on one hand and 3 fingers on the other hand, right? Now that's why they count in base 5. I can almost guarantee you their computers are also going to be binary, right? Why? Because it's the simplest, right, and least error prone. But is it going to matter? Do the algorithms suddenly become faster because the aliens are doing it with only 5 fingers? No. Well, that's hold on to that thought, because that's another issue entirely. Log base b can always be converted to any other log base. How? Log base a of x. All you need to do is apply the change of base formula. Log base a of b. This here is just a constant, right? I could re-express this as some constant sitting out front, log a of x. Right? All bases, all logs are the same to within a constant. It doesn't matter if you're counting with fingers, 10 fingers, on and off in binary, or 5 fingers with the alien races. You can convert from one base system to the other. You have the exact same number of operations to within a constant. Right? Alien computers are no more faster, algorithms on alien computers are no faster than they are on ours. They're just, the technology itself is just faster. Now, one exception to this is Roman numerals. What base system is Roman? Right? 1, 2, 3, 4, 5, right? You basically have, and then 6, right? This is almost what's called a unary system, right? So ignore all these larger ones. A unary system would only have one symbol, a tick mark. 1 day that I've been in prison. 2 days, 3 days, 4 days that I've been in prison. 5 days. 6, 7, 8, 9, 10, 11, 12, 13, 14, 15. Right? Really, really inefficient way of writing things down, because now the answer to how many strokes or how many ticks does it take to represent 5 is 5. How many ticks does it take to represent 5 billion? 5 billion, right? That's not efficient at all. And that's also why, if I tried to do this, is there such thing as a log base 1 of x? No. Why? Because when we move it back, 1 to the b is equal to x. Is that ever going to work? 1 raised to the power of b is only ever going to be 1. And that's why unary systems don't work mathematically. Right? All right, good. Going back over here. So the naive answer, of course, was 1. The correct answer is that the size of of a number is the number of bits required, bits required to represent it, i.e. n is equal to log base 2 of x, where x is the number that you're trying to represent. Now, in CS, all of our bases are base 2. So we write log of n. Right? We're self-respecting computer scientists. We're not mathematicians. Dirty mathematicians would say what the base system for mathematicians is? No, not 10. That's for grade school arithmetic, it's base 10. Base e, why e? Because the first derivative of e has a coefficient, coefficient of 1. Right? Everybody knows that, right? E to the x, what's the first derivative of that? E to the x, oops, sorry, no. Come on, there we go. E to the x, e to the x. There is a 1 out front though, and that's what happens when you have the natural log, right? Just so that we know, what is, if you take another base, what is, well, we'll get to that later. All right, okay, let's erase all this. Okay, so after we've identified the input size, let me move, oh, no, I don't want this. The next step is to identify the elementary operation, right? Ultimately, what we want to do is we want to characterize an algorithm's amount of work or the amount of resources that are required to actually execute this algorithm, right? So what we need is, we need one operation to represent this work, right? We want only one. I mean, an algorithm can be doing a bunch of things. It could be doing a bunch of comparisons, and then it could be doing a bunch of additions and a bunch of subtractions and a bunch of multiplications or whatever. It could be doing 50 different operations. We want to winnow it down to exactly one. right? In general, we want the most common or most expensive or most relevant operation. You might have an algorithm that does multiple operations, but you need to focus on one, right? And if you focus on one and you get one analysis, that's perfectly fine for that operation. If you focus on a different one and you get a different analysis, that's fine for that operation. There are some operations that you generally don't want to pay attention to. For example, any operation necessary for the control structures of the algorithm are generally not relevant. Right? So for example, consider the typical for loop that you write when it comes to a basic algorithm. I need to shut that off. All right, let me go over here. For int I equals 0, I is less than n, I plus plus. Right? What kind of operations are we doing here? There's an assignment. Right? There's a comparison. There's an addition. Are any of those relevant? Well, first of all, what about the assignment here? Is that really relevant? That just happens once at the beginning of the loop, right? This comparison certainly is happening more often. This addition is also happening more often. But even more relevant to that, we're doing something inside this loop, right? Whatever we're doing inside this loop, every time we do it, we're doing one comparison. Every time we do this something, we're doing one addition. So if we do start counting these, they're just going to be proportional to what we're actually doing in the loop anyway. So no, we don't want to look at things that are necessary for the control structure of the algorithm. We want to look at things inside of a loop, what the algorithm is actually doing. Okay? All right. So for example, what are some things that an algorithm can do? Examples. Right? Comparisons. Searching and sorting, which is what we're going to look at or revisit, for say, from computer science 1. Arithmetic operations. So, for example, additions and subtractions. Now, I grouped those together. Why? And is there really any difference between an addition and a subtraction? A subtraction is simply what? Adding a negative number, right? What about multiplications and divisions? Why did I put those two together? What is a division? It's a multiplication by a reciprocal, right? Or an inverse. Right? But between these two groups, which one is more expensive, do you think? Probably multiplications, because multiplications are just simply iterated additions. 5 times 10, you add 5 10 times, or you add 10 5 times, right? Whichever way you want to look at it, right? Yeah, go ahead.
But if you had to choose just one, wouldn't you choose addition?
It depends. Again, it depends on the algorithm. If you do a multiplication, but then you're doing a bunch of additions, right? You only did one multiplication, but you're doing n additions. That's the more relevant one, right? Whichever all three of these considerations come into play here. Whatever is the most common, the most relevant, or the most expensive, right? And again, there's not necessarily just one right answer. There could be multiple acceptable answers there. Right? Finally, say a list, a node traversal, node or vertex traversal in a list or graph, right? That's what we started out with. When we looked at the performance of a linked list, we were doing work. We quantified that work by saying that when you go from one node to the next node, that's our work. How many times are we actually doing that? Right? And then finally, step 4, not finally, but finally for this part, is step 4, the analysis, right? You analyze the algorithm to determine how many times the elementary operation is executed with respect to the input size, n. That is, we come up with a resource function. There we go. Now, I'll ask this again. Have you talked about functions in 235 yet? Hopefully? Okay. I'm going to call it f, right? You could call this t if you were trying to quantify time. You could call it m if you were trying to quantify memory. I'm just going to keep it generic and say that it's f. Right? And it's going to map a domain to a codomain. It's going to map n. What is that thing there? The what? N is a set, right? What set is that? It's n for natural numbers. There you go. And natural numbers are 0, 1, 2, 3, ... Why not negative numbers? What we're going to do is we're going to map to right arrow to math BB z, or not z, but reals positive. All right, there we go. Okay. So why are we mapping the natural numbers to positive reals? Let's take a look at that domain first. Natural numbers. What is that capturing? That's capturing input sizes to a resource measure. Right? Why natural numbers then? Have you ever heard of an input size of negatively sized input? Like a list with -5 elements in it. Does that make any sense? No. Of course, you can have an empty list. That's why we include the natural numbers, right? Can you have a list of size 3.5? 3 elements and then a half element? No. So that's why we restrict it to just non-negative integers. Now, the thing that we're mapping to is the positive reals. What if we map to all the reals? So here's an algorithm. You run it on an input size of 50, but it takes negative time to run. That means you start running it right now and your answer appeared 5 minutes in the past. Does that make any sense? Nope, that'd be pretty cool, and then you've just invented time travel. If your resource measure is power, have you ever heard of a computer that you run it on an input of size 50 and it generates power rather than consuming power? Nope. Like I said in this morning, if you find that, start mining some Bitcoin really quick, because not only are you mining Bitcoin, you're also generating power rather than consuming power, right? So then you could hook that back into the grid and get some money for it or something, right? This process may involve coming up with a summation, solving it, etc. Right? It may, the most advanced algorithms are going to require fundamental, mathematics, right? Proving something is correct or proving something is efficient might require advanced field theory or advanced algebra or something like that. We're not going to get that fancy here. We're going to keep it simple, but it might involve coming up with a summation and coming up with a closed form solution for that summation. Okay. In general, you want to focus on the worst case scenario, right? To provide an absolute upper bound on the resources required to run an algorithm. Right? The first example that we're going to look at here is a prime example of it, linear search. We've seen this before. In fact, we kind of did it before, but we didn't do the pseudo code for it. I think we did a pseudo code for finding the maximum or the minimum value or something like that. So let's go through this at least 4-step process. I haven't covered the 5th step yet of asymptotics. We'll save that for next week. What I want to do is I want to go through this 4-step process with several examples now. The first example is going to be, linear search. So as with all pseudocode, I'm going to clearly label the input and label the output. So the input is simply going to be a collection A. And I'm also going to give the elements a name, A1 through AN. Right? Again, good pseudocode. I've kept this general. I'm not saying that this is a set of integers or an array of strings or something like that. I'm just saying that this is a collection of elements. I've also encoded how many elements there are by writing good pseudocode here, by putting that, labeling them. There's how many elements are in here? N elements. That's going to help us to identify the input and the input size really, really easy. Right? And a key, K. Remember, we're searching, this is our haystack, and this is our needle in the haystack. Right? Our output will be an element, and I'll go ahead and use the mathy way of doing this, a sub I in A, such that a sub I is equal to the key. Right? I didn't use equals equals. I didn't use PHP equals equals equals, the strict equality operator. I didn't use the dot equals method on a string, right? I'm keeping it as generic and mathy as possible. Okay? Pretty straightforward at this point. For each a sub I in A, if a sub I is equal to the key K, output a sub I. Right? And you're done. Except that it could result in an unsuccessful search, right? So what would we output in that case? If we go through every single element and we don't find what we're looking for, what should we output? Null? That's a programming language concept. Some languages don't have null, right? -1 because of indexing. Some languages allow you to use negative index values. PHP, right? I'm going to use another math symbol called phi. Phi is often a placeholder for saying nothing, right? It's not the same thing as an empty set, although some people do use phi as the empty set erroneously, I believe, at least in my opinion, but there you go. Oh, really? Why? You got... All right, if you are typing LaTeX, use empty set. Do not use phi. It looks like phi, but it's a little bit different, right? I'm using phi here not as the empty set, but as a placeholder for nothing, right? But a lot of people do this, right? That they do use that for the empty set. Why, when you've got perfectly good LaTeX to do it for you? Well, I mean, it's virtually no different, right? Phi or phi, right? It's a handwriting difference, right? All right. What I'm going to do is I'm going to label these line numbers because it's going to help us in our analysis. We'll be able to reference the thing on line 4, right? Or something like that. Okay. So let's go through the step-by-step process. What is the input? Now here you have 2 inputs, but we want to keep it simple and we want to only focus on one. Would it be appropriate to focus on just the key? There might be a collection of 10 elements and 1 key. There might be a collection of 1,000,000 elements, but yet still 1 key. Right? So what's changing? The size of the set, not the size of the key. There's only just one. Right? So our input here will be the collection A. Right? What's our input size? N. That was nicely encoded already with good pseudocode. 3. What is our elementary operation? And here's where the line numbers are going to come in and help us. Well, I do have a for each loop, right? And there is some cost to iterate over the collections. We've seen that cost. If you have a naive algorithm that iterates over the collection in a linked list and you do it badly, you're waiting 20 years for it to compute, right? If you were to actually write this out, say in a traditional for loop, for I equals 0, I is less than n, I plus plus, You do have comparisons. You do have additions. But is that something that we should be paying attention to? Stuff is going on inside that loop. That's the stuff we should be focusing on. Right? So probably not line 1. If A is equal to K, okay. Maybe that comparison right there. Should we focus on line 3? That only ever happens once. Once you output something, you're done. That terminates the algorithm. Likewise with this output, right? So my elementary operation will be the comparison on line 3. Now the question becomes, how many times is this comparison on line 3 executed with respect to the input size, n? N times? Right. Oh, okay. Let's think about the worst case. Let's think about the best case. And let's think about maybe some other things. Let's think about that best case first. When is this going to be super, super quick? You stop and you find it at 1, right? A1 is equal to K. In which case, how many comparisons did you make to find that out? 1 comparison. Can you be so naive and optimistic that it's always going to be that way? Probably not. What about the worst case scenario? So n comparisons. How did you get there? So in other words, you found it at the last spot that you looked, or phi, no such element. Right? I would agree. In both of those instances, you end up doing n comparisons. It's not the first one, it's not the second one, it's not the third one, ... It's not the last one. You did n comparisons to find that out. We could go a third way, somewhere in between. What would you call that? Something like that? Average case? Right? The naive way of looking at that would be what? Taking n, the best case, the worst case, and then just simply averaging them, right? And you would get something like n divided by 2. The real way to do this is to come up with what's called an amortized analysis. You would have to define a probability distribution on a successful search versus an unsuccessful search. Then you would have to define a probability distribution on what's the probability of finding it at the first index? What's the probability of finding it at the second index? What's the probability of finding it at the third index? ... And then you would have to find the probability distribution that maximizes the number of comparisons. Right? Once you've done all that work, very, very rigorous mathematics, not that difficult of mathematics, but rigorous mathematics, maybe a page or 2 of math, guess what? You come up with the same answer. About n divided by 2. All right?
That's good.
So is there really a difference, though, between n and n divided by 2? What's the only difference? It's this 1/2, right? It's that 1/2 sitting out front. Ultimately, do we care about constants? Nope, because you upgrade your hardware, and those constants become even smaller, right? And we don't want to look at algorithm analysis from a particular hardware, particular language, etc. Okay. Okay. So the worst case scenario here will end up being n. And step 5, skipping ahead before we've covered it, we end up writing that this is an order n algorithm. Big O analysis. This is actually the Greek letter omicron, but it's indistinguishable from our own O. So we just write O. In fact, LaTeX doesn't even have an omicron, and you just use an O. But we'll get there next week. Yeah.
Why not just use the worst case scenario then?
We do. We want to look at this. Right? Sometimes you want to look at that average case. In fact, by the end of the day, I'll show you an algorithm in which wow, that actually is important. We should pay attention to the average case scenario in some instances. Right? But in general, you can't go wrong with worst case scenario because it's at least as big as the average case. Right?
That would be the best case scenario at least.
Yeah, you don't want to do the best case scenario all the time. Right? All right, so more examples. Okay. Another example is something that you've seen before, selection sort. Now, you might not remember it exactly, but let's go ahead and go through a really quick example. 4, 7, 3, 2, 5, 1. Right? 1, 2, 3, 4, 5. Okay, I'm just missing 6. That's all right. Selection sort worked how? Remember, it goes through and selects the minimum element. So it starts at the first one and assumes, okay, this is my minimum so far. That's not less, so 4 is still my minimum. That is less, so now 3 becomes my minimum. Right? 3 is 2, that's less, so now 2 becomes my minimum. 5, that's not less, so 2 is still my minimum. 1, oh, okay, that's less, so that's my minimum. What do I end up doing? I end up swapping 4 and 1. Right? Those ended up getting swapped. At this point, this list, that thing is where it needs to be. Now, what does the rest of the algorithm look like? You start at the next element, go through, and you find the minimum element there. Once you've found that minimum element, you swap it with that element. So, 7, 2, get swapped. At this point, this part of the list is done and sorted. Next iteration, 3 is your minimum, and there's nothing else that's minimum, so you end up swapping it with itself. Okay? Next iteration, 2, 3, there. That's the best fix I can do. I don't know if there's an undo. Good notes? Anybody know good notes? Or where's the undo button? Do you know? Is there an undo? That's all right. I'll look at it later. Anyway, then we go through, find the next minimum, 4, and swap it with 7, at which point everything is done, right? We've got 4, 5, 7. Now we do go one more iteration here, find that 5 is the minimum, swap it with itself, be done. When we're done with everything except for the last element, what can you say about that last element? It's sorted, it's where it needs to be. Okay? So, let's codify this in pseudo code. Okay? Clearly label the input a collection A of elements A1 through AN. And again, I'm not saying what they are. I'm not even saying how you compare them. That's a job for a comparator, right? Output A sorted. Okay. That process that I just described was kind of 2 loops, right? For the list starting at the first element, find the minimum, put the element there. That's 1 loop. The next iteration, you start at the second element and find the remaining minimum element. Third iteration, you start at the third element and you go through and find the third smallest element, etc. So we start at I running from 1 up to something. What is that something? Remember, we didn't have to go all the way, right? Once the first n minus 1 of them were sorted, that last guy was where he needed to be. So we can stop when? N minus 1. Right? Now, for each iteration, we find the minimum. Find the minimum among AI through AN. Right? Because everything before it has already been sorted. So what I'm going to do is I'm going to set my minimum, min, to be AI. Again, we're going from AI to AN. So I can start by assuming that the first one is my minimum. And then I can go through the rest of them. For j, running from I plus 1 through n, remember, here we do have to go all the way because the minimum could be at that last position. In fact, the example that we did, it was at one point. 1 was the last one. Right? If the jth element is less than a min, then we found something smaller. So a min takes on the value aj. After we've found the minimum, where do we put it? We swap it. Here's the minimum. Here's the ai element. All we have to do is swap those. For that, I'm just going to use plain old English. Swap a sub I and a min. Okay. There's our pseudocode for selection sort. Let me number them. 1, 2. I will number the comment just so that you can make reference to the comment if you really wanted to. 6 and 7. Right? That's why I use the graph paper theme. It helps me a little bit to align it. Otherwise, we'd be writing in like a curved circle here, right? Okay. So that 5-step process. 1, what's the input? That's pretty easy. There's only 1 this time, no key. What's the size? N. And again, that was encoded in the input. What is the elementary operation here? So there's lots of stuff going on, lots more stuff than the than the linear search, right? Anything here? Again, it's necessary to the control structure of the algorithm. Right? Comment? No. An assignment? Yeah, go ahead.
In order to sort stuff, that may be necessary as well.
To what?
In order to swap things.
Oh, that's down here. We'll talk about that in a second here. But what about this assignment right here? It's really not the most common because we've got another for loop down here that's doing stuff, and it's doing a lot more stuff than just one thing, right? So look for the more common operation. Again, necessary for the control structure of the algorithm. Ignore it. The comparison on line 5. Okay. Comparison line 5. Now let's go ahead and continue here, even though we've kind of decided on this. What about this swap? Swaps are expensive, depending on your memory, right? If it's a cache hit, a miss, yep, you may want to minimize that. That becomes an engineering question, right? And if you wanted to analyze this algorithm with respect to the number of times it swaps something, that's a perfectly reasonable choice. If you have an engineering concern that memory accessing is much more expensive than a comparison, then let's go ahead and analyze it with respect to the number of swaps. And there have been instances in real life, we have Garmin speakers come in all the time, and one of the things that they talk about is how they intentionally use a slower sorting algorithm in some of their products because it results in fewer memory accesses. And in an embedded system, the memory access is way more important than the processing stuff. Right? So they will tolerate more comparisons because their processor is fast versus as long as you can minimize the number of memory accesses. Right? Okay. Then 4. How many times is the comparison on line 5 executed with respect to the input size n? Add them all up. Now here's where the math comes in. And what we're going to do is we're going to make it somewhat easy by not worrying about the algebra until later. Okay? And what I mean by that is let's focus on line 5 first. If you ignore everything else, right, and you only focused on line 5, how many comparisons are there on that line? Just one. Right? There's one comparison on line 5. Now, let's zoom out a little bit. Line 5 is part of this code block here that is tied to this for loop. The entire inner code block is going to be executed for every iteration of that for loop. How many times is that for loop executed? Again, don't worry about that. Set up a summation. It's going to run from j, running from I plus 1 up to n. So just put that into a summation. J equals I plus 1 up to n. Right? Now this is part of another code block. Right? That code block is encapsulated right here, and it is tied to this for loop up here. So make another summation. That summation runs from I equals 1 up to n minus 1. Right? And at that point, you're done by adding up all of the terms. All you need to do now is solve for this. This was line 5. This was expanded out in line 4, and the entire thing was from line 1. All right? Yeah, go ahead.
What about line 3?
Line 3, that's not, we discounted that as our elementary operation, so it's irrelevant. Right? You're only focusing on one operation. Just like line 7, right? We're ignoring that because we didn't want to do swaps, we wanted to do comparisons. Right? So, let me rewrite that summation. It's 1, j starting at I plus 1 up to n, and I starting at 1 up to n minus 1. Okay? You don't have to write the parentheses are implicit when you're doing summations. You work inside to out when you're solving summations. So what we're going to do is we're going to focus on this inner summation here first. Right? How many ones are there? So let me write out j running from I plus 1. There was one there. I plus 2, there was one there. I plus 3, one there. Dot, dot, dot. All the way up to n, and there was one there. So how many ones are there? In terms of I and n. N minus I. Why n minus I? If I were to expand this out and start it at 1 instead of starting at I plus 1, 1, 2, 3, dot, dot, dot. I, then I plus 1, then I plus 2, I plus 3, dot, 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 n. How many are there total here? N. How many are there from here up to here? I. So therefore, how many are left over here? N minus I. Right? What plus 1? We started at I plus 1, if that's what you mean. Right? So this simplifies to I running from 1 up to n minus 1 of n minus I. Summation of sums is equal to the sum of summations. So you can break this up. I equals 1 up to n minus 1 of n, and then take the negation out front. I running from 1 up to n minus 1 of I. Hopefully that first one is really easy. N plus n plus n plus n plus n. How many times? 1 up to n minus 1. So, n minus 1. Right? That's this one right here. Now, what about this one? 1 plus 2 plus 3 plus 4, because I is iterating, right? I is going from 1, 2, 3, 4, all the way up to n minus 1. So 1 plus 2 plus 3 plus 4, that sounds familiar. That's the what? That's smart guy. In the first section today, we called him that guy, right? So I'm going to go ahead and repeat that smart guy's formula. Right? Summation of I equals 1 up to n of I is n times n plus 1 all over 2. Right? That smart guy again was Gauss. Right? but I like that smart guy's formula, right? All right, but I'm not going up to n, am I? Or I'm going up to n minus 1. So when I plug n minus 1 into n and n minus 1 into n, what do I end up getting? All over 2. The second one is half the first, so when I subtract them out, I get, well, it's simpler than that. Right? It's just the second term. The second term is half the first, so that's all I need. Right? Now this is order n squared, because as we've already looked at this before, the highest order term there is quadratic. We can characterize this as a quadratic function. Right? Again, big O analysis next week. Yeah?
Is this like similar with limits and mathematics?
Oh, it's exactly limits. Now you got me thinking that I'm going to do the limit method here in this class, even though, have you done the limit method in 235? Oh, okay. Limit as n tends towards infinity of f of n over g of n. Right? One of three things can happen. It can converge to 0, it can converge to a non-zero constant, or it could diverge off to infinity. If it goes to 0, what is that kind of saying about the growth rate of the ratio of these two functions? The one on the bottom is growing way faster than the one on the top, and so we say that f of n is big O of g of n. G of n is the faster growing function, right? If it converges to a non-constant or a non-zero constant, that means that it converges to 3. That means their growth rate is the same, and we write f of x n equals theta g of n. Right? Otherwise, if it diverges off to infinity, that tells you that the numerator is growing way faster than the denominator, and therefore f of n is big omega of g of n. Right?
I don't need to understand that now, do I?
No, that's the calc interpretation of these things, right? And then you get a whole bunch of equivalencies. Like, for example, this is equivalent to saying that g of n is big O of f of n. Right? You're just swapping them back and forth. That's omicron, theta, and omega. Right. No, wait. That proof. When we get to proofs, trust me, you will want to prove things by the limit method. But I'm going to make you prove it by using algebra, and that's more tiresome. All right, one more example, and we have a good amount of time here. So, insertion sort. Okay. Insertion sort is a different type of sorting, not a different type of sorting algorithm, but a different strategy to the sorting algorithm. So again, 3, 4, 1, 7, 2, 8, let's say. Okay. So here's the idea. You start at the beginning with an array or a list of size 1. By definition, that is sorted, right? Then what we do is we go to the rest of it. Right? I'm looking at this. I'm not looking at the rest of this right now yet, though. I'm looking at the next element right next to it. 4. Where would 4 get inserted into this list of size 3 here in order to be where it needs to be? There are two options. You could insert it on over here, or you could insert it over here. Which one do you do? Right here. In other words, it is right where it needs to be. Right? Now, now we look at the next one here. In fact, what I'm going to be doing this entire time is I am going to be putting this into a temporary variable, 1, so that I can have room to move stuff. Okay? So now that's in a temporary variable. And what I'm going to do is I'm going to compare this temporary variable to each one moving from right to left. Right to left. So 1 and 4. Where would I put this relative to 4? I would put it before 4. So what I'm going to do is I'm going to shift 4, oops, over because I've made room for it. Right? Now I'm going to compare it to the next one, 3 and 1. 3 would go in front of 3, or sorry, 1 would go in front of 3, so what I'm going to do to 3 is shift it. And now at this point, I have nothing else to compare. Oops. So where does 1 belong? Right here. And I end up putting it where it belongs. I end up inserting it where it belongs. At this point, this part of the list is now sorted. I continue. 7. I look at 4. Oh, I don't need to do anything with that at all. Right? So, that, oops, come on. There we go. There. That ends up being my new list. Next iteration, I look at 2. 2 needs to be, it goes to the left, 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 and finally that's where I end up getting, it ends up getting inserted. Throughout the entire process, I was shifting these things up because I put 2 into a temporary variable up here. Right? That's the idea. Okay? Help me out with this. Let's write the pseudocode for it. So my input will be as before, a collection, A1 through AN. My output will be A sorted. Okay? Now, codify that. Where did I start? Remember I started and said, well, the first one, that's just a list of size 1, so it's sorted automatically. So where do I actually start? At the second one. For I running from 2, and here I go all the way up to n. Because at the very end, I need to make sure that that one is where it needs to be by inserting it. Right? I'm going to insert the ith element where it needs to be. ... How do we do that? Let's put it into a temporary variable so that we don't lose it. And we've made room for it because it doesn't matter now if we overwrite it by shifting things over. Right? Where do I start shifting things? So what? Remember we worked, this is the AI element, and so we started here and shifted things over, shifted things over, shifted things over. We went from right to left. So a sub I would start it at -1. Right? Now, do I always go all the way to the beginning? Nope. Sometimes I get lucky and I don't even have to shift anything. So that tells me I probably want some sort of a while loop. Right? While what condition? Again, I've taken this thing out and put it into this temporary variable up here. I'm going to be comparing aj and this temporary variable. If t, the temporary variable, is less than aj, then I need to shift things over. So if t, the temporary variable, is less than aj, then how do I shift that one thing over? aj plus 1 will take on the value aj. I'm just taking aj and moving it forward to aj plus 1. Right? Move it forward, move it forward, move it forward, move it forward, until this is no longer satisfied. Right? I do have to set myself up for the next round by modifying j, and since I work right to left, I decrement it. Right? Now I still have this temporary variable right here, and it needs to go where it belongs, so I insert it by doing what? A sub j, after I've broken out of this loop, is going to take on that temporary variable. I left myself some room here for a reason. What happens when you get down to the end? Yeah, you don't want to fall off the edge of your cliff of your list. So while j is strictly greater than 1, and that holds. Okay. Let's clean this up a bit. There we go. There. That's what nice pseudocode looks like in LaTeX. This is from the computer science book computer science 1 book from last semester. Okay. I think I did everything correct, except that I did use x here instead of t. Had I to do it over again, I would use t because it's a temporary variable. Right? Okay. Let's analyze this with the time that we have left. 1, what's the input? A. 2, what's the input size? N. 3, what's the elementary operation? So, again, lots of stuff here. That's necessary for the control structure of the algorithm. Ignore it. What about these two things right here? It's just an assignment. They're not even the most common assignments, right? There's another assignment down here. So you might be thinking, wait a second, I do want to do assignments because assignments for some reason are expensive. Okay, fine. 1, 2, 3, but this one's going to be repeated over and over and over again, right? So if you want to come up with a more complex formula where you've got, say, some a n plus, or a n x squared plus b n plus c, and come up completely with all of these coefficients, be my guest. But you'll find out that if we have something like this, a n squared plus b n, does this really matter in the context of this one over here? Absolutely not. So let's ignore those as well. Now, this one is necessary for the control structure of the algorithm because it prevents you from falling off the face of the list and coming up with a index out of bounds exception or something like that. It's not necessary for the algorithm itself. It's only for the control structure of the algorithm. This, however, that's a comparison, right? Think about what you're doing. Don't lose the forest for the trees. You are looking at elements in a list and saying, is this one greater or is this one greater? If they're out of order, then I need to swap them, right? If they're out of order, I need to shift it up, right? So that's our actual comparison right there. What about this? That's just an assignment that's part of shifting, right? If this, in fact, these are not always executed. Only when this is true do these actually get executed. So for every execution of this, you have at least this. In fact, you have at least more of these, right? You have at least one more than you have of these. So this one is probably our most relevant thing here, right? And this one is just an assignment. You can roll that into those up there if you want to. So I'm going to say the comparison on line 4. Okay? Yeah?
The assignment be more expensive, though, in general.
Not really. I mean, think about, even on a real computer, what are you doing? You're calling a comparator. The comparator function is probably going to be a lot more expensive than simply loading something up into a register in a computer, right? Because that's going to involve a whole function called passing parameters, creating a stack frame, swapping in and out of contexts, et cetera, et cetera. So even from the engineering standpoint, this is probably going to be a lot more expensive. Okay. All right. Analysis. How many times is that executed on line 4 with respect to the input size? We don't have a nice little for loop here anymore, do we? Or we can just make a summation. So let's do the same thing that we did with linear search. And let's think about the best case scenario and the worst case scenario, and then maybe the average case scenario. So best case. And I'm just going to give it to you. Suppose that we have 1, 2, 3, 4, 5, 6. Now let's simulate insertion sort on this. This is already sorted. It's a list of size 1. So now this is our element right here. How many comparisons do we make to ensure that it's already there? 1. And we end up not inserting it anywhere. We don't shift anything. Now we go to the next one, and we look at, oh, it's already where it needs to be. How many comparisons did I make there? Oh, sorry. Just one more. Right? And you can start to see the pattern emerge. 4 is where it needs to be, so I only make one comparison to find that out. I don't end up shifting anything. 1, 1, 1. How many in total here in this particular case? 5. If there were, in general, n elements, the best case scenario has how many comparisons? N minus 1. Right? So it looks linear to me in the best case. Now here's the worst case. If the best case is that it's already sorted intuitively, what do you think the worst case is? Sorted, but in reversed order. Right? Now let's simulate insertion sort here. No comparisons here because it's of size 1. 5 needs to be shifted over before 1. That was one comparison. And we end up with 5 and 6. Now we look at 4. One comparison to see that 6 needs to be shifted over. One comparison to see that 5 needs to be shifted over. And finally 4 just gets put where it needs to be. There were, if you were counting up with me, 2 comparisons to do that. And we are left with 4, 5, and 6. We'll do one more here. 3 goes before 6, goes before 5, goes before 4. I counted 3 comparisons there to get 3, 4, 5, and 6. Now, simply predict. What about 2? That's going to be 4 comparisons. 1, 5 comparisons. So, add all of those up. And then generalize this so that you have n. It's that guy's formula again, that smart guy's formula, right? This is going to end up being n times n plus 1 all over 2. Right? That's the worst case scenario, best case scenario. So worst case, if we're only interested in that, we're done, and we say that this is order n squared. Step 5 next week.
Wouldn't it be n minus 1 times over 2 inside?
Nope. You have to. You're. Oh, sorry. I get what you're saying. That we stop short, right? That we only go up to n minus 1 here. So yes, you're right. I can erase. I can fix my mistakes. There you go. It's exactly the same thing as selection sort. Mm-hmm. Thank you. That is a technical detail there, but at the end of the day, do we care? It's just going to be order n squared. Yeah.
So basically,
From that perspective, they're both the same. But now, let's take off our computer science hat and let's put on our engineering hat. Right? Is there a difference? Okay. Yes. Why? Swapping. Well, shifting is a form of swapping. Right? We're just copying this one over, and then copying that one over. So there is memory accessing. That is an issue on both of them. But let's think about it in terms of, say that there's A1 through AI minus 1, and we've got AI right here. Right? Let's think about this in terms of average. You're not always going to have a set that, or a list that is completely sorted. You're not always going to have a list that is completely sorted in reverse order. You're going to have randomized lists, right? So you're not going to get the best case scenario of making one comparison. You're not going to always get the worst case scenario of making I minus 1 comparisons. On average, again, let's just do the hand wavy solution here. How many comparisons can you expect to make on the ith iteration here? About half, right? Instead of comparing it to I minus 1, which would be the worst, best would be 1. Let's go ahead and add those together and average them, right? We'll do it the naive way, which turns out to be the exact same thing. Exact same answer, I should say. Oops. It ends up being, can't get it right, I divided by 2. Right? And intuitively, you can kind of see this because on average, you're going to go half, sometimes you're going to go exactly half the distance. Sometimes you're going to go over here, but other times you're going to go over here, and those two things tend to cancel each other out, right? And so you're left with I divided by 2. You do that n times, right? So we end up with a summation that looks like that, more like this. And what was our summation before? Oh, right here. Oh, we didn't write down the summation, but it would end up being, according to the loop right here, 2 to n. So I equals 2 up to n. Right? I don't like dealing with small numbers, so let's just go ahead and expand that out. That's at least as big, right? And it makes it nicer. So that smart guy's formula, not exactly the smart guy's formula because we do have this 2 right here, but what can we do with our summations? That's just a constant that can come out front. Now it's the smart guy's formula, and it ends up being 1/2 of the smart guy's formula, and plus 1 all over 2. In other words, if I expand this out again, it's going to be 1/4 n squared plus 1/4 n. Now, is there a difference between that and what we had with selection sort? I have to go back a long way there. Well, it wasn't 1/4, it was 1/2. So on average, insertion sort is doing 1/2 fewer comparisons. So now with our engineering hat on, can we say that there's a difference? Yeah, this one is twice as good, right? It has half as many operations on average if you look at the average case scenario, right? And so that kind of analysis is useful quite often when you can argue, well, yeah, asymptotically they're both the same thing, but in practice, if you're forced to use selection sort or insertion sort, which one are you going to use? Insertion sort. But now in practice, what should you do? Oh, what is binary sort? All right, a lot faster sort. What are some of those? There is binary insertion sort, but unfortunately, it's basically no better than insertion sort. You can use binary search with on the section that's already sorted, but you still end up having to shift stuff, so to make room for it. So you're kind of screwed anyway. In practice, what do you do? What are some other algorithms that we've heard about for sorting? Oh, okay. You jumped right to the conclusion, like always. Conclusion. Don't. Right? Don't roll your own. Use the libraries. Use libraries. All right. So what do the libraries use? Quick sort, merge sort. There's another one, Tim sort. That's Python and Java 8 and up, right? There's also something very nice that we'll look at the end of the entire course, something called Heap Sort. And I love doing that as the last thing in this course because it calls all the way back to the theme of this course, which is that smart data structures and dumb code are a lot better than the other way around. This is a perfect sorting algorithm that all you do is you put stuff in and you take stuff out. And that's it. Dumb code, smart data structure, and it comes out sorted, right? It's like you throw everything into a box, you push this magic button, and you dump it out, and it's all in order, right? It's because it's a magic box called a heap. All right, any questions? Otherwise, we will continue there with step 5, asymptotic analysis on Tuesday.